factorization be in xenon tetrafluoride? This is problem 1054C. First of all, you've got to find the CBA. That's the one that has the fewest atoms, so in this case, it's going to be xenon. So that one goes in the middle, and you try to attach as many things to that as you can. In this case, there are only 4 other things, so you can just put those 4 things all around the xenon. Let's make this bigger. Okay, how about that? Remember in class we did the H2SO4, and in that case everything except for the 2 H's were attached to the central sulfur. And now here it's a little easier because there are only 4 other things, and those 4 things fit all around the xenon. Now, next step is, how many valence electrons are there for all these atoms? Well, just look at your periodic table. Xenon is in that last group, so it has 8 valence electrons, and fluorine is a halogen in the next to last group, so it has 7 valence electrons, 1 less than Lotto, where 8 is Lotto. Now you are God. Put the valence electrons where you think they should go, and remember, a bond is 2 valence electrons, 1 from one atom and the other from the other atom. Lone pairs are dots. Usually, in this class, they're pairs of dots, and you can guess at how many dots or how many bonds you should draw by the rule. It starts with an O. It has to do with the Lotto. Yes, it's the octet rule. Even God follows the octet rule. Sometimes. Now let's count these. Looks like there are 32 electrons here, and that's including 2 electrons for each bond. 32 is not enough. We're supposed to have 36, so we're missing 4 electrons. How can you possibly put 4 more electrons on this? Well, remember, xenon, in the middle there, is eligible for an expanded octet. Now, xenon can have a maximum of 8 times 2. Remember, in class, the rule is that if there's an atom that is eligible for an expanded octet, the maximum number of electrons of eligibility is 2 times the number of valence electrons that element naturally has. So in this case, 8 times 2 is 16. We don't need that many. We just need 4 more, so we put 4 more. 8 plus 4 is 12, less than 16, so that's okay. Now you count how many electron groups are hanging off of the xenon. 2 lone pairs, 4 bonds. That's 6 groups. Remember that table that Sam drew on Sunday? Hybridization for something with 6 groups on is sp3d2. Now sp3d2, you can see that 2 on the D plus 3 on that P plus the invisible 1 on the S makes 6. 2 plus 3 plus 1, that's 6. 6 groups. And just for fun, let's have a look at the geometry here. There are 6 groups hanging off the xenon. It's sp3d2, so the geometry is, first of all, electronically, it is octahedral. This is the maximum number of groups you could stick onto anything in chemistry. But what about the molecular shape? I mean, there are only 4 atoms hanging off of the xenon. So, molecularly, it is not octahedral. Molecularly, what would it be? Well, you know, when you have some octahedral geometry, the angle between each group is 90 degrees. But the top and the bottom groups have 90 degrees to the left and 90 degrees to the right. So that top group that I draw right there, that has a total of 180 degrees of room to play. That bottom group, same thing. 180 degrees of elbow room. So that means that xenon is square planar because those lone pairs, they take up the most room. They need the most room. So they'll take the top and the bottom. And those fluorines, remember fluorine is the most electronegative, so it's also the most compact atom in a bond. So there it is. Square planar. Those fluorines can live 90 degrees apart from each other and they'll be okay. Any questions? Please ask on Moodle.